Welcome to today's Explainer. We are jumping right into a really fascinating and, honestly, often misunderstood part of cement manufacturing: particle fineness. We're going to look at how a seemingly simple measurement, literally just how small a particle is, dictates everything from plant efficiency to the final strength of the concrete that builds our world. Now, you might be wondering, doesn't grinding materials as fine as possible just make the absolute best cement? It's a pretty natural assumption to make, right? Well, actually, scratch that. As we'll see today, heavy industry operates much more on a Goldilocks principle. Grinding something too much can actually be just as disastrous as not grinding it enough. So here's our game plan for today. We'll start with the core concepts, move to the raw mill for an early warning, check out the coal mill where we feel the fire, hit the cement mill for the dual approach, and finally look at finding the perfect balance. All right, section 1, the core concepts, residue and Blaine. Before we actually walk through the plant, we gotta nail down our two hero metrics. First up, we have residue. Think of residue as essentially a search for the chunky, unground pieces that got left behind. We measure this by passing the ground material through these standard test sieves, usually right around 45 to 90 microns. Whatever doesn't pass through, well, that's our residue. So a high residue number literally just means you've got way too many coarse particles. Now, let's contrast that with our second metric, Blaine. While residue is looking for the big chunks, Blaine measures the total specific surface area of the particles. And why does surface area matter? Because hydration, you know that chemical reaction that happens when cement actually meets water? That starts at the surface. Finer particles mean a higher total surface area exposed to the water, which translates to much faster hydration and better early strength. Moving right along to section 2, raw mill, the early warning. Let's step into the very first stop on our plant tour. In the raw mill, the goal isn't just to crush rocks. It's about producing a raw meal that can chemically react efficiently once it's inside the kiln. Here, we rely heavily on measuring residue. And ask any experienced engineer, they'll tell you straight up, raw meal residue is absolutely not just some random lab result. It is a critical early warning system for your entire plant. Just look at the sheer scale of the chain reaction when this goes wrong. It's like a row of dominoes. If your raw meal has too many coarse particles, say some chunky limestone, they need way more heat and time to react. That leads to poor burnability and leaves uncombined free lime hanging out in your clinker. To fix that, operators have to burn more coal, which skyrockets your specific heat consumption. Suddenly, your massive factory is literally throttling its own throughput, all because a few microscopic coarse particles slip through the raw mill. Crazy, right? Okay. Section 3, coal mill, fueling the fire. Over here, the physics and the objectives change completely. We are no longer focused on chemical mineral reactions. Now we are all about rapid, complete combustion. But just like the raw mill, we still use residue to measure fineness. If you have high coal residue, meaning coarse coal particles, they take way too long to heat up and burn. This causes unnecessarily long flames, chaotic temperature fluctuations in the kiln, and dangerous spikes in carbon monoxide. You're basically just blowing unburnt carbon and a ton of wasted energy right out of the system. So you might be sitting there thinking, let's just grind the coal to absolute dust then, right? But overgrinding coal introduces severe explosion risks. It's super dangerous. Plus, it demands massive amounts of mill power and drying energy, but gives you almost zero additional combustion benefits inside the kiln. Once again, it is that Goldilocks principle. We need the optimum fineness. Not too chunky, but definitely not dangerously fine. Next up, section 4, cement mill, the dual approach. You can kind of think of the cement mill as the boss level of the plant. The raw materials have been burned into clinker, and now we're grinding that into the final product. Unlike the raw mill or the coal mill, where we mainly just watched our residue, the cement mill demands a dual approach. We have to monitor both Blaine and residue. Why? Because now we're optimizing for how the final product actually performs out in the real world. But wait, what if we just push for maximum surface area, maximum Blaine, just to get the absolute fastest reaction? Well, doing that totally crashes your plant efficiency. Your power consumption shoots up, your mill output drops, and your grinding media wears out way faster. And even worse for the customer, excessively fine cement actually increases the water demand when mixing concrete. That can seriously compromise the structural integrity. Definitely not what we want. Let's look at a real-world example from the source data to really lock this concept in. 3,400 square centimeters per gram. I just want to pause for a second to let the sheer microscopic scale of that target surface area sink in. That is the exact target Blaine or this specific grade of cement. And this brilliantly illustrates exactly why Blaine alone is never enough. Check this out. We have cement A and cement B. Both have hit the exact target Blaine of 3,400. If a plant manager only looked at Blaine, they'd say, great, both of these are identical, perfect batches. But measure the residue at 45 microns. Cement A has 4% coarse particles remaining. Cement B has double that, 8%. And here is the conceptual payoff for our whole journey today. Because cement B has that hidden 8% of coarse chunks, it's going to fail the customer. Those coarse particles cause a much less uniform performance, which leads to lower early strength and slower hydration. This proves, without a doubt, exactly why both parameters, Blaine for surface area and residue to catch those lazy, coarse chunks, are absolutely mandatory in the cement mill. Finally, Section 5, Finding the Perfect Balance. Let's tie this entire plant-wide journey together. In the raw mill, our main objective is clinker formation, so we focus heavily on residue to remove chunks that simply won't chemically react. In the coal mill, our objective is combustion, so we focus on residue again to ensure fast, stable flames. But in the cement mill, the objective is final product performance, so we must use both Blaine and residue to ensure rapid strength development while avoiding the coarse particles that ruin uniformity. As you can see, the objective at each stage perfectly dictates the measurement we use. Which leaves us with this final thought. In modern heavy industry, successful fineness control is almost never about pushing a dial to the absolute maximum. It is not about having the highest Blaine or the lowest residue. The real engineering magic, it's all in the balance. It's about asking yourself, are you finding the optimum balance between product quality, production efficiency, and energy consumption? Thanks so much for joining me on this explainer, and I hope this gives you a whole new appreciation for the incredible microscopic precision behind the cement that builds our world.